Hi learners, I am Vijaya Kumar Gurrala, the faculty of ECE department. Now I am going to discuss about the BJT transistors. As we know that the BJT transistor has the three terminals, emitter, base, collector. So in a circuit, if you want to operate as an amplifier or for whatever, these the three terminals to be connected in a different way. One terminal can be used for the input, the other terminal can be used for the output, and one more terminal can be connected for the common means for input and as well as an output. So based upon that, we have the three configurations. One is common base configuration, the other one is common emitter configuration, and the next one is common collector configuration. So in a common base configuration, base is common, so means emitter can be used for input and the collector can be used for getting output. Likewise, we have the three configurations for a transistor. So this is how we can connect the transistor in a circuit. So the first one is for the common emitter. See here, emitter is common to input and output. So this is we consider as an input. This is can be we can consider as for an output. So base is for input, collector is for output. Likewise, if we consider a common base, so here it is the base is common, the other two terminals emitter. So emitter is for input, collector is for output. Likewise, the common collector. So in a common collector, collector is taken as a common to input and output. So input you can apply at base and output you can collect at emitter. So likewise, here we have the three configurations of a transistor. Now we'll discuss each and every one in detail. So before we get into that, here we'll discuss about some key points or common points for all the configurations what we are. So here throughout the discussion, all currents are considered in a conventional direction. Will not consider the electron flow. All the current directions which are mentioned in the next coming slides are these are a conventional flow according to that whole flow, and I consider an NPN transistor, not a PNP transistor. So accordingly, the PNP and NPN, I'll tell you for an NPN, for a PNP, the polarities will be changed. So what we will consider is these characteristics input and output, these to be determined for each configuration for common base, common emitter, common collector. So these are to be mentioned: input characteristics, output characteristics. So as we know that the characteristics are nothing but the VA characteristics, volt versus the current, or IV characteristics, current versus the volt. On x-axis we consider voltage and on y-axis we consider a current. In addition, one parameter is we will consider it as for reference. So what parameter to be considered for reference for input and as well as for output? So for that, to avoid that ambiguity, that's why I'm considering some key points. I'm telling you the key points. What are the points here? So these characteristics to be determined in line with the H parameters. So what are H parameters? We will try to write input voltage as a function of input current and output voltage. Likewise, output current can be written as a function of input current and output voltage. So when you are trying to consider an input characteristics, it is a plot between input voltage versus input current. So input voltage, input current, what parameter to be taken as a reference? This is the one. Always I1 and V2 taken as a reference. So these are the independent variables, and this V1, I2 are the dependent variables. So here in this, already we covered V1 and I1. I1 is already covered. What to be considered? V2 as a reference. Output voltage. Likewise, output characteristics. So you can consider output characteristics. It's a plot between output voltage V2 and output current I2. So it's an I2 versus V2. And what parameter to be taken as a reference? We already covered V2. And what else is I1? So I1 as the reference. So this is how we can determine or we can explain the configurations in terms of input characteristics and output characteristics, and along with that some other things are required. When you are explaining about input characteristics, you should consider a general transistor equation, that is VCE equal to VCB plus VBE. Likewise, when you are considering an output characteristics, so you should consider the current relation, that is IE equal to IC plus IB. In addition, output current equation is IC equal to alpha IE plus IC naught. So these relations we can consider. Along with that, in that output characteristics, you should consider or represent active region, cutoff region, saturation region. Active region, as we know that the transistor has two junctions, emitter base junction one junction, the collector base junction is the next one. Okay, so the two junctions, if this is emitter base junction and assume that it is a collector base junction, active region means this is to be forward biased and this is reverse bias, so that the transistor acts as an amplifier. Likewise, cutoff region. So in a cutoff region, both junctions are reverse biased. In saturation region, both junctions are forward bias. So here the transistor acts as an off switch, totally off, there is no output current, and here it is a maximum current, so it is an on switch. So this is how you can operate a transistor. So these are the common points to be followed or considered for each configuration. Coming to that individual configuration, the first one is the common base configuration. So let us see what is common base configuration. As we know that the three terminals, one is common, the other two, one is for input, the other one for output. So likewise here common base, so base is common to input and output. So here emitter is input and collector is output. So at input, at emitter will apply input, at collector will take output. So how the polarities, how you connect a supply to that a transistor in this common base. So always emitter junction, remember that emitter junction forward bias, collector junction reverse bias. So emitter junction means emitter base, this is NPN. Throughout the discussion, I am considering NPN transistor only. So for an NPN, emitter base junction, emitter is N type and the base is P type. So apply a forward bias. So forward bias means for an N, you should apply negative terminal of battery, and the P will apply a positive terminal. So this makes it as a forward bias. So this is what this, a supply, input supply, and here it is output supply. Output junction is reverse bias. So what is here? A collector base, this has to be reverse bias. So reverse bias means collector is of an N type and an NPN and the base is of a P type. So this NP, another PN junction, this has to be reverse bias. So how we will give a supply? For an N we should apply a positive supply, and for P we should apply a negative. For a PNP it reverses. So basic thing is emitter junction is to be forward bias. So whether it is an NP or PN, accordingly you should apply a battery connection. And collector junction is reverse bias. Simply we consider it as, some textbooks may refer it as input junction, output junction. Input junction forward bias, output junction reverse bias. Don't get confused about all those things. So NP, make this as a forward bias. Here NP, make this as a reverse bias. So here in this situation, that input voltage, here it is the voltage between emitter and base, this is what VEB, and the output voltage is, it is taken between collector and base, so that output voltage is we consider as VCB. And the input current, what is that input current? It is to that input terminal emitter, so this IE is input current, and output current is at collector, so that output current is IC. So we have that for a transistor in this configuration, the four terminals input current, input voltage are IE, VEB respectively. Output voltage and output current, output voltage is VCB, output current IC. So based upon this, we should discuss its operation. That operation is done with the help of input characteristics and as well as output characteristics. As I told you, input characteristics, it's a plot between input voltage VBE or VEB, input current IE, with what is considered as a reference output voltage V2. So these are the common points for every configuration. So output voltage is VCB. Okay, so before you increase that input supply, start to increase that output voltage. So initially assume that output voltage is at 0 volt or 1 volt. Okay, so when output voltage is 0, unbiased output junction. So in at that unbiased output junction, if I start to increase VBE, what is that VBE? VBE is nothing but one of the PN junction. So you are as you are increasing the input supply, what it makes that PN junction forward bias. So that's why the input characteristics are nothing but a diode forward bias characteristics. So as you increases that input supply at here, this makes the diode forward bias, and the voltage across this emitter and base is 0.7 for silicon, 0.3 for germanium. So here in this consideration, I am considering a silicon transistor. So that's why it is 0.6. So for a accordingly, for a small instant of change in the input voltage, there is a large swing in output current. So here the input voltage is up to 0.6, then the current starts increasing like this. Now what if we increase VCB? So initially we consider VCB equal to 0. Now it is increased to 10 volts. So if I increase VCB to 10 volts, what is happening? VCB, what is that VCB? It is the potential between collector and base. We are trying to make that collector junction reverse bias. So as you increases that reverse biasing of that collector base junction, what will happen? The depletion width at the collector base increases. So as VCB is increased by keeping that VEB constant, the width of the base region is decreases. The depletion width at the collector bases increases, as we know that the doping levels of collector and base are different. Base is lightly doped, a collector is moderately doped. So accordingly, the width of the depletion layer penetrates more into the base than that of the collector. As it is more penetrate into the base region, the effective base width is decreases. As the base width decreases, what will happen? The recombination decreases. As recombination decreases means IE increases. So that's why as VCB increases, the emitter current increases and the characteristics are tends towards left. This is what we consider as an early effect. That is what we will discuss in detail here. Early effect or the base width modulation. So what it means, as VCB increases, as the magnitude of collector voltage increases, we are trying to increase the reverse bias potential at collector and base. So the depletion layer width at that junction is increases. So due to the different doping levels of that base and collector, the depletion layer penetrates more into the base than that of a collector, so that the effective width of the base is decreases. So the base width is decreases. This is what we consider as early effect. So this has some consequences. What are the consequences? The first one, there is a less chance of recombination. So if there is as the width of the bases decreases means more number of charge carriers from electron that enter into due to the forward biasing of emitter base junction, majority charge carriers from the emitter are enter into the base then into the collector. So since the effective base width is decreases, there are less number of charge carriers to recombine. So the recombination rate here it is decreases. So alpha increases. As we know that the alpha range is some 0.95 to 0.98. So alpha is almost equivalent to 1. Like that the case will happen as you further increases. And the second point is the charge gradient is increased within the base. See here, the charge gradient is increased, so that the current of majority charge carriers injected across the emitter junction increases. And what about the third point? For extremely large voltages, which means as you are keep on increases the reverse bias potential at collector base, that width, the depletion layer width, we keep on increases, so that the effective base width is decreases at one point of time, the base disappears. So that is what the base width may be reduced to 0. So this causes breakdown in the transistor, and this phenomenon is called a reach through or punch through. Reach through. So that width decreases and it is reaches to emitter. That's why it is called it as reach through or the punch through. The punch is applied by the reverse bias potential at the collector base junction. So this is what input characteristics of a common base configuration. Now coming to the output characteristics, as we know that IC output current equation is IC equal to alpha IE plus IC naught. IC naught is reverse saturation current. So this can be rewritten as IC equal to alpha IE plus IC B naught, common base, reverse saturation current at common base configuration. That is how it looks like. So here output characteristics. Output characteristic, as we discussed, it is a plot between output voltage versus output current by keeping input current as a reference one. So here for a common base configuration, output voltage VCB, output current IC, and considering incremental steps of references input current IA. So first try to slightly increase that IE. Initially IE is equal to 0. When IE equal to 0, what is IC? IC equal to IC B naught. So your output current is nothing but the reverse saturation current. So no current. As IE equal to 0, no input current, no potential at input. Output, we are making that VCB, reverse bias. Okay, so input no potential, now the current is ICB naught. This is what the condition we consider it as cutoff region. In that case, both regions will be in reverse bias. Now, as you keep on increases IE, as IE is increases, what will happen? As we know that the reverse saturation current is very less. So alpha times IE is very much greater than ICB naught. So your IC will be approximately equal to alpha IE. And we know that one more point, alpha is in the range is 0.95 to 0.98. So it is approximately nearly equal to 1. So IC and IA is similar together. Both are similar, means same. So that's why as you keep on increases IE, the characteristics are mostly flat. Why? Because IE is approximately equal to alpha times IE. Alpha is nearly equal to 1. So that's why the characteristics are flat. And this region we consider it as active region. Active region, as you are increasing the reverse biasing at the output junction and increasing that input current. So means forward biasing at that input junction, reverse biasing at output junction. So this is what active region. Then one more region to be explained. As I told you that at output characteristics, you should explain about active region, cutoff region, and the saturation region. So active we have covered, cutoff we have covered, the leftover one is the saturation region. So what is saturation region? The both junctions to be at forward bias. So when it will be forward bias, as IE increases means input junction forward bias means that emitter junction forward bias. When will be that output junction is forward bias? So you should apply the reverse potential to this 0. As you increases this potential, this makes that output junction reverse bias. So in a saturation region, what we want, output junction is also to be a forward bias. So you should apply the reverse to that of that reverse potential. So the characteristics which are left to that origin, so that makes that output junction is also a forward bias. So how will be that characteristics? So in that case, for a little amount of change in that output voltage, there is a large amount of change in output current. Nothing but our diode forward bias condition only. Maybe if you see the characteristics seems to be in quadrant 1. Actually the characteristics are, as we are increasing the reverse bias potential. So increasing the reverse bias potential means we are trying to make that output junction reverse bias. So how will be that characteristics of reverse biasing a transistor diode? They are like this. This is V, this is I. So the characteristics are like this. This has to be in the third quadrant. But for a generalized purpose, either for a PNP or an NPN, for that purpose, the characteristics are drawn in a quadrant 1. Don't get confused about by referring the other textbooks. So here, these are nothing but the similar only. The same Q3 is mapped to Q1, the quadrant 1, for a positive voltage and for a positive current. See, this is an NPN transistor. So for this NPN transistor, this is the supply is positive negatives, and you if you place a voltmeter here, this shows a positive reading. If it is a PNP transistor, so PNP transistor, so for a PNP transistor, if you want to make that output junction reverse bias, you should apply negative potential here and the positive potential here. So for that, to get the reading of output voltage, if you place a voltmeter, that voltmeter shows you the negative reading. So for an NPN to PNP, that voltage readings, the polarities will be changed. So for a generalized thing, what we have considered is all the characteristics are drawn in quadrant 1 only. Positive voltage, positive current. Likewise for that output characteristics also. Positive voltage, positive current. In next video, I will discuss with you the other two remaining configurations, common emitter and common collector configurations. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.